Welcome to the Deep Dive. Today we're plunging into the universe of particles that are everywhere, passing through you right now, yet somehow remain almost entirely invisible.
Sounds fascinating.
We're talking about neutrinos, the universe's most elusive particles. They're mysterious, incredibly abundant.
And potentially holding the keys to some huge cosmic questions.
Exactly.
Yeah.
Our guide for this exploration is some really interesting text we've been poring over, digging into what these ghost particles are.
And how they link to the hidden universe.
Right, so we're going to use this as our map, basically, to unpack what neutrinos are, why they matter so much even though they're so hard to pin down, and how they might reveal secrets about reality we just can't see any other way.
Absolutely. And it's important to remember, while they hardly interact individually, their sheer numbers and, fundamental properties give them massive implications, huge implications for how we understand everything from the heart of stars to the very existence of matter itself. This deep dive really highlights just how significant these tiny elusive particles truly are.
Okay, so let's start right at the beginning then. What exactly is a neutrino? Where did this idea even come from?
Well, the concept of the neutrino was actually first predicted, way back, in fact, 1930.
1930, that feels incredibly early. What was going on then that made someone propose a completely new invisible particle?
Yeah, it was basically to solve this puzzle in radioactive beta decay.
Okay.
So when certain atomic nuclei decay, they shoot out an electron, or maybe it's antimatter version, a positron.
Right.
But when physicists measured the energy of the particles coming out, it didn't add up. It didn't match the energy the nucleus lost.
So energy was just disappearing.
It seemed like it.
Yeah.
And Wolfgang Pauli, who predicted it, he was really hesitant to break the law of energy conservation. It's a fundamental principle.
Sure. Can't just throw that out.
Exactly. So he famously suggested there must be another particle being emitted, one we couldn't see or detect back then, carrying away that missing energy.
A ghost particle right from the start, just to save a fundamental law. That's fascinating. So what are its defining characteristics, according to the text?
Well, the text lays out a few key ones. First, they are electrically neutral.
No charge.
No charge. And that's a huge part of why they interact so rarely, They don't feel the electromagnetic force, which governs most everyday interactions.
Okay, thanks.
They are also incredibly light, nearly massless.
Nearly. Not completely massless.
Right. For a long time, people actually thought they were massless, like photons, particles of light. But as we'll definitely get into, discovering they have even a tiny bit of mass, that turned out to be incredibly important.
Okay, holding on to that thought. What else?
And maybe the most crucial thing for their elusiveness, they interact only via the weak nuclear force and gravity.
Only those two.
Just those two. And compared to the strong force holding nuclei together, or electromagnetism, well, the weak force is incredibly short range and, frankly, weak.
Right. Hence the ghost name.
Precisely. That's why a neutrino can zip through literally light years of solid lead without hitting a single thing.
Light years of lead. That is genuinely hard to wrap your head around, just sailing through. And I've heard they aren't all the same either. They come in different types, is that right?
That's right, yeah. They come in 3 known flavors or types. There's the electron neutrino, the muon neutrino, and the tau neutrino.
Okay, electron, muon, tau. Got it. Now, here's where, for me anyway, it gets really interesting and maybe a bit mind-bending. The source highlights that as they travel, they can actually switch between these flavors.
Yes, they oscillate.
Oscillate.
Yeah, a neutrino that starts its life as, say, an electron neutrino can, as it flies through space, spontaneously change into a muon neutrino or a tau neutrino, and then potentially back again.
Whoa.
This phenomenon, neutrino oscillation, it was a monumental discovery, just huge.
And that's what led to the Nobel Prize.
That's right, the 2015 Nobel Prize in Physics for Takaaki Kajita and Arthur B. MacDonald. Their experiments showed definitively that this happens.
Why is that discovery so monumental? I mean, okay, they switch flavors. Why is that such a big deal?
Well, because it tells us 2 incredibly important things directly. First, it's absolute proof that neutrinos must have mass.
Okay, connecting back to the nearly massless point.
Exactly. If they were truly massless particles, like photons are, quantum mechanics basically forbids them from oscillating. They couldn't change identity.
Right.
So the very fact that they do switch confirms they have mass, however tiny it might be.
Okay, that's one big thing. What's the second?
The second is, well, it's huge, the original standard model of particle physics.
Which has been amazingly successful, right?
Incredibly successful, yes. But that model predicted neutrinos were massless and therefore couldn't oscillate. So finding neutrino oscillation, that was the first definitive experimental proof that the standard model is incomplete. It's not the final story. It's probably the strongest evidence we have that there is new physics beyond our current best theory of fundamental particles and forces. It forces us to rethink the rulebook.
So these tiny, almost invisible particles were the first real crack in the standard model. That completely changes how I think about them.
Okay, so if they're everywhere and they're proof of new physics, where do they actually come from in the cosmos?
They actually have quite a few birthplaces, surprisingly diverse sources across the universe. The text points out several key ones.
Like what?
Well, they were created in enormous numbers, just moments after the Big Bang itself, primordial neutrinos.
Okay, from the very beginning.
Then there's our sun and pretty much every star out there. They're basically massive neutrino factories.
So fusion.
Exactly. Constantly produced by the nuclear fusion reactions happening right in the stellar cores.
Makes sense. What else?
Supernovae. You know, those catastrophic explosions of massive stars?
Yeah.
They unleash an absolutely enormous burst of neutrinos. Something like 99% of the star's gravitational collapse energy is carried away by neutrinos in just a few seconds.
99%. That's staggering. It really is. And then closer to home, even natural radioactive decay happening down in the Earth's crust produces some neutrinos.
Huh. Even from Earth itself.
Yep. And cosmic rays, high-energy particles from space hitting our atmosphere, generate showers of them, too.
So they are truly raining down on us.
Yeah.
From all directions, all the time. And the source emphasizes just how many there are.
Oh, yeah. After photons, the particles of light, neutrinos, are the most abundant matter particles in the entire universe.
More abundant than electrons or protons.
Way more abundant, yeah. Trillions of them are passing through your body right now in the time it takes you to blink.
That's kind of wild to think about.
It's this incredible contrast, isn't it? They're absolutely everywhere, completely pervasive, yet almost impossible to detect. That's what makes them so fascinating.
Okay, so given that incredible abundance, what kind of impact do these particles that barely interact with anything actually have on the universe? How can something that passes through light years of lead actually do anything significant?
Well, that's the paradox, isn't it? Even though they interact so weakly individually, their sheer numbers mean that collectively they do exert influence.
Okay.
They play a really crucial role in how stars live and die, particularly in the mechanics of supernova explosions.
The explosions we just mentioned.
Yes, they help carry away energy from the collapsing core, which is actually necessary for the explosion to, well, explode outwards.
Huh. So they're essential for that process.
Seems like it. They also factor into the creation of elements, both during the Big Bang nuclear synthesis and later in stars.
Element formation, too.
Mm-hmm. And on the very largest scales, their tiny mass, even though it's small, might have subtly influenced how cosmic structures, like galaxies and galaxy clusters, formed and evolved over billions of years.
So they're shaping things on the grandest scale.
In a subtle way, yes. The text uses a great analogy, actually. It calls them the ghostwriters behind the universe's story.
I like that. Ghostwriters of the cosmos.
Yeah, subtly influencing the plot from behind the scenes without being easily seen.
Okay, but if they interact so rarely, how on earth do scientists actually detect them? You said it's almost impossible. It sounds like trying to catch smoke with tweezers.
It really is. Detecting them is genuinely one of the great technological challenges in physics. It pushes the boundaries.
Why is it so hard? Just the weak interaction?
Primarily, yes. Because they interact so rarely, your only chance is to have an absolutely massive detector.
Massive how?
Filled with a huge amount of target material. Could be water, could be ice, could be liquid scintillator. You need tons and tons of atoms.
Just to increase the odds that one neutrino might bump into one nucleus.
Exactly. You're playing a numbers game. More targets means slightly better odds of a rare interaction.
Right, so size matters.
No, and you have to shield these detectors from pretty much everything else in the universe.
Shield them? From what?
Cosmic rays, which are constantly bombarding Earth, natural radioactivity from the surrounding rock, all sorts of background noise that could easily create a signal that looks like a neutrino interaction but isn't.
Ah, so you need quiet.
Yeah.
Really quiet.
Extremely quiet. That's why these huge experiments are often built deep underground, under mountains.
Like the examples in the text. Tell us about some of those detectors. Super Kamiokande.
Yes, Super Kamiokande, or Super K in Japan. It's this enormous tank deep under a mountain filled with 50,000 tons of ultra-pure water.
50,000 tons of water.
Ultra-pure water, yeah. And lined with thousands of incredibly sensitive light detectors.
Wow. An IceCube. That's the one in Antarctica.
That's the one. IceCube uses a cubic kilometer of the natural Antarctic ice cap itself as its detector medium.
A cubic kilometer? That's immense.
It is. Again, they drill long strings of light sensors deep into the ice.
An SNO++ in Canada.
Right. SNO+K, the Sudbury Neutrino Observatory, that one uses heavy water, which has special properties that allow them to distinguish between the different neutrino flavors. It's been crucial for studying neutrinos from the sun and looking for supernova neutrinos.
Okay, so these are structures on an absolutely epic scale, just to catch a few of these ghost particles. So when a neutrino does, finally, against all odds, interact in all that water or ice, what do they actually see? How do they know it happened?
They look for a very specific signature, a faint flash of light called Cherenkov radiation.
Cherenkov radiation.
So when a neutrino hits an atom in the water or ice, it usually produces a charged particle, like an electron or a muon.
Okay.
Now, if that charged particle is traveling faster than the speed of light in that medium, faster than light travels through water or ice, not faster than light in a vacuum.
Right, the cosmic speed limit still holds.
Correct. If it's going faster than light in the water, it emits a cone of light, kind of like the optical equivalent of a sonic boom.
A shockwave of light.
Exactly. It's typically a faint blue glow. And all those light sensors lining the detector are there to pick up these tiny, brief flashes.
That's the signal, that faint blue glow.
That's the primary signal, yes. The pattern and timing of the light hitting the sensors tells them about the energy and direction of the original neutrino, and sometimes even its flavor.
Incredible. Just a flash of blue light tells you a cosmic ghost flew by.
Well, flew through and finally interacted.
Right, and this unique ability of neutrinos to just pass through almost everything. That means they offer us a window into parts of the universe that light just can't reach, doesn't it?
Exactly. This is where that phrase from the text, where light is blind, neutrinos can see, really hits home.
How so?
Well, think about light. Light, being electromagnetic radiation, gets stopped or scattered very easily. By dust, by gas, by magnetic fields, by the incredibly dense cores of stars.
So lots of things block light.
Lots of things. But neutrinos, they interact only weakly, so they just sail right through all that stuff, basically unaffected.
So they can come directly from places light can't escape from.
Precisely. This lets us see into places totally opaque to light, like the nuclear furnace right at the center of our sun where the fusion happens.
We can see the sun's core with neutrinos.
Effectively, yes. We detect the neutrinos produced there. Or, even more dramatically, the collapsing core of a massive star just seconds before it explodes as a supernova. Light is trapped inside until the explosion breaks out, but the neutrinos stream out almost instantly.
So we get an inside view of the explosion starting.
An inside, real-time view. They can also travel across vast, dusty stretches of the universe, carrying information directly from distant, violent events like exploding stars or active galactic nuclei, without getting distorted or absorbed along the way like light does.
Wow. Any other hidden places they might reveal?
Well, there's hope they might offer unique ways to search for things that are even more elusive, like dark matter.
How could they help with dark matter?
Some theories propose exotic types of neutrinos, so-called sterile neutrinos, which would interact even less than the regular ones we know.
Even less. Is that possible?
Theoretically, yes. And these sterile neutrinos are actually a candidate particle for dark matter. Neutrino experiments are searching for signs of them.
So they're really opening up entirely new ways of observing the cosmos. It feels like a whole new sense.
It really is. And they're a crucial piece of this growing field called multi-messenger astrophysics.
Multi-messenger, meaning?
Meaning we're no longer just studying the universe by collecting light waves, radio, infrared, visible, X-rays, gamma rays.
Right, the traditional way.
Now we're combining information from totally different kinds of cosmic messengers. We use light, yes, but also gravitational waves, those ripples in space-time itself.
From black hole mergers and things like that.
Exactly. And neutrinos. Each one, light, gravity waves, neutrinos, brings a unique perspective, carries different information about the same cosmic event.
So seeing the same event with all three gives you a much richer picture.
A vastly richer, more complete picture. It's like going from seeing in black and white to seeing in full color, maybe even 3D.
Okay, so considering all of this, their unique properties, their ability to travel anywhere, What are some of the biggest, most fundamental cosmic mysteries that our text suggests neutrinos might actually help us solve?
Oh, there's some really profound questions tied directly to neutrinos. I mean, some of the biggest questions we have.
Such as?
Well, perhaps the deepest one is, why does matter exist at all?
Okay, that is a big question. How on earth does a tiny neutrino connect to that?
Well, think about the Big Bang. Our best theories suggest it should have created equal amounts of matter and antimatter.
Okay, equal amounts.
But if that had happened and they were perfectly equal, they would have annihilated each other completely.
Poof, leaving just energy.
Leaving just energy, yeah. No galaxies, no stars, no planets, no us. The fact that we live in a universe overwhelmingly dominated by matter with hardly any antimatter around is a huge puzzle.
So why didn't they all annihilate? Where did the antimatter go?
Exactly, and neutrinos might hold a key. There are subtle differences being investigated in how neutrinos and their antimatter counterparts, antineutrinos, behave, particularly concerning something called CP symmetry violations.
CP symmetry? That sounds complicated.
It's basically a rule about how particles and antiparticles should behave if you swap their charge and mirror their interactions. If neutrinos violate this symmetry in a specific way,
Yes.
it could have tipped the balance in the very early universe, leading to a tiny excess of matter surviving the annihilation, enough to build everything we see today.
Wow. So neutrinos could literally be the reason we exist.
They could be a crucial part of that reason, yes. It's a major focus of experiments like DO.
Okay, that's mind-blowing. What other big questions?
Another huge one. What is dark matter?
Right, the invisible stuff making up most of the universe's mass.
Exactly. We know it's there because we see its gravitational pull, but we can't see it directly. The text mentions those sterile neutrinos we talked about earlier.
The even ghostlier ones.
They are a theoretical candidate. If they exist and have the right properties, they could actually be the dark matter. They'd be incredibly hard to detect, fitting the dark profile perfectly.
So searching for sterile neutrinos is also a search for dark matter.
In a way, yes. It's one avenue of searching.
What else?
And as we touched on earlier, they're absolutely key to understanding what lies beyond the standard model of particle physics.
Because their mass and oscillation already broke it.
Precisely. That discovery already proved the standard model isn't the final word. So studying neutrino properties, their exact masses, how they oscillate, whether they violate CP symmetry, is like looking through a window into that new, deeper physics. We're directly probing physics, perhaps at energy scales we can't even reach with our current particle accelerators.
There are messengers from beyond the standard model.
You could put it that way, yes. They point the way forward.
Any more practical applications?
Well, potentially. Predicting supernovae.
Yes. You mentioned the neutrinos get out first.
Right. When a massive star collapses, it unleashes that huge burst of neutrinos before the visible light from the actual explosion breaks free and travels to us.
How much warning could that give?
It could be hours, maybe even days, depending on the details. If we could detect that early neutrino signal reliably,
we could tell astronomers, quick, point your telescopes over there.
Exactly. It would give them precious warning time to observe a supernova right from the very, very beginning of the explosion. That would be invaluable data.
From explaining why matter exists to maybe predicting exploding stars, that's an incredible range of impact. So what's next? What's on the horizon for neutrino research? What upcoming projects does our source highlight?
Yeah, there are several major international experiments either under construction or being planned, really pushing the boundaries of detection and measurement.
Like which ones?
Well, there's the DUNIR project, the Deep Underground Neutrino Experiment based in the U.S.
DUNI. What's its goal?
It's designed to study neutrino oscillations with unprecedented precision. They'll shoot an intense beam of neutrinos over 800 miles through the Earth, from Fermilab near Chicago to massive detectors deep underground in South Dakota.
Through the Earth. Wow.
Yep. To study how the flavors change over that long distance. And it's specifically looking for that CP violation, the matter-antimatter asymmetry clue.
Okay, DUNI is a big one. What else?
There's JUNO, the Jiangmen Underground Neutrino Observatory in China.
DUNO.
Its main goal is to solve the neutrino mass hierarchy. Basically, we know neutrinos have mass, and we know the differences between the masses, but we don't know the absolute ordering which one is lightest, which is heaviest. JUNO aims to figure that out.
Another piece of the puzzle beyond the standard model.
Exactly. And then there's Hyper Kamiokande, or Hyper K in Japan.
A bigger Super K?
Essentially, yes. A detector significantly larger than Super Kamiokande, maybe 8 times the fiducial volume.
That's enormous.
It will dramatically increase our sensitivity. More chances to catch neutrinos from distant supernovae, study solar neutrinos, proton decay searches, and again, probe CP violation.
So the quest continues with even bigger, better tools. Now, these massive projects, they sound focused on fundamental physics. But the source mentions potential broader impacts too. It's not just about cosmology and particle physics.
That's right. Often, the cutting-edge technology developed for these giant, super-sensitive experiments finds applications elsewhere. It pushes innovation.
Like what, for example?
Well, think about potential advances in nuclear monitoring.
Monitoring reactors.
Yeah, potentially using neutrino detection to verify nuclear non-proliferation treaties by monitoring the activity of nuclear reactors from a distance, since reactors produce a lot of antineutrinos.
Huh. Interesting. Anything else?
There's research, still early stages, into using related particle detection techniques for medical imaging, and the incredibly sophisticated AI and machine learning, the data analysis techniques develop to sift through the petabytes of data these experiments generate.
They must need serious computing power.
Oh, absolutely. Those advanced analysis techniques could definitely have wider uses in other scientific fields or even industry.
So, wow. We've really journeyed quite a way here, from a particle that was just predicted, almost reluctantly, to save a fundamental law.
The law of energy conservation.
Right. To discover it's this pervasive cosmic ghost whose really bizarre properties like changing identity mid-flight revealed cracks in our most successful theory of physics.
The standard model, yeah.
And finding them requires these epic feats of engineering giant tanks deep underground, cubic kilometers of ice.
Just to catch a few faint flashes of light.
And through that effort, we've seen how they offer this unique lens on the hidden universe, seeing into star cores and maybe even hinting at dark matter. And they might hold clues to mysteries as absolutely fundamental as why matter, why we exist at all.
It's quite a story for such an elusive particle.
It really is. So thinking about all this, about the trillions of these tiny, nearly undetectable particles streaming through you right now, constantly, carrying messages from the heart of stars, from the edge of the universe, maybe even hinting at physics beyond our wildest dreams. How does that change your perspective on a hidden universe that's all around us and within us? What does it really mean that the most abundant matter particle after light is something we barely feel, but which holds such profound secrets? Something to think about.
It truly underscores how much we still don't know, and how often the key to understanding the grandest cosmic scales lies hidden in the properties of the very smallest things we can study. The hunt for the ghost particle secrets is definitely far from over. It's an exciting time.
Thank you for joining us on this deep dive.